Hi everyone, welcome to our first podcast on yes on Bosch Future Mobility Talks. Today, I'm glad that we will talk with few of their great specialists. But first, let me tell you a few things about Bosch. Probably everyone knows Bosch, but just for an info, there are four business sectors: mobility solutions, industrial technologies, consumer goods, and energy and building technology. And also, what I recently find that Bosch strategic objective is to facilitate connecting living with products and solutions that either contains AI or being developed or manufactured with its help. So this is really interesting, and you will see during the next presentation. Also, a few things about Bosch engineer center from Cluj-Napoca, and not only. There are three centers in Romania. One and the main one is in Cluj-Napoca. There's also a Jucu factory, a factory in Jucu. And recently they opened some development center in Bucharest. And of course, the headquarters of Bosch Romania are also in Bucharest. So mainly these are few things about Bosch. And let me go now to our first presentation. I try to be short. So, hi, Ovidiu.
Hello, can you hear me fine?
Yes, everything is fine.
Good.
Yes, so Ovidiu will talk about geometric computer vision and automated driving. So, Ovidiu, the stage is yours.
Yeah, thanks for the introduction and let's jump into the topic. So today we will discuss a bit about geometric computer vision and what is this geometric computer vision, what is good for. So let me go a bit in the next slide to discuss a bit about the agenda that we have today. So first of all, I will introduce myself a bit to know who I am and what I'm doing in Bosch. Then we will discuss about what people expect actually when we discuss about computer vision. Yeah, because in general public we have a certain expectation when you say computer vision. Then further we will start discussing about the geometry, meaning the relation in between the 3D scene and the actual scene understanding of a computer vision based algorithm. Of course, this leads us to the pinhole camera model that we use, and the relation of the mathematical model with the 3D point cloud that we have in the real world. Then we will discuss about what is a road surface estimation computation, and that is done via the vanishing points. We will see what is that, what is a vanishing point, and then we will use this exactly for the original purpose to do 3D reconstruction and see how this helps in the overall computer vision. So let's jump in. So some words about me. I'm a team leader in Cluj, leading geometric computer vision activities. I'm here in Bosch since 2015, and here you can see some examples of what we do in terms of computer vision and especially geometric computer vision. So we do depth estimation, meaning we know for each pixel in the image what is a specific depth. So not only if it's a vehicle, but it's a vehicle 10 meters away. We do surface estimation. We know how the road in front of us looks. We do free space estimation, meaning as an automated driving vehicle, you want to know where you can drive and where you cannot drive. And of course, we have to validate all these computer vision algorithms. And how we do that, we compare our reconstruction with a laser scanner and we have to process those points. So this is all about the background where I'm activating it and I'm working here, and my scope is to lead this team to develop state-of-the-art algorithms. So let's go and discuss about what is the expectation when we talk about computer vision. So first of all, of course, we have an image. Yeah. So this is a real image from a driving scene of an automated driving vehicle. So what we expect to have here, we expect to have an image, and what we do with this image actually, we plug it as an input for a big neural network, which uses deep learning techniques to actually do what? To actually detect objects, for example, where are the vehicles in that scene, detect, for example, the guardrail, you know where the direction of driving ends, and you detect also the lane markings. So you want to know actually where you are able to drive there. And this is in a way true. Of course, we have to do all these steps, but that's not all about it. So now we will discuss exactly why it's not all about computer vision, and I will discuss about the other side of the computer vision, the geometric part. Yeah. So this is the detection side. More insights in this will be presented by my colleague Lucian afterwards. But now let's speak about what is actually not so obvious when you do computer vision. So now, actually, let's imagine you have a vehicle. We call it ego vehicle because it's our vehicle, yeah. And we have a camera in that vehicle. Then, of course, on the road you have traffic. You have some vehicles in front of us that we have to detect and decide what we do. So in that the same particular scene, we have some viewing angle where you can see the object in front of us, which is the red object, red rectangle in the picture below. Then of course you have a region of the side view of the camera which looks to the ground and see, okay, here is my surface, what I have in the surface, I have lane markings, and of course other vehicles like the yellow one, they are actually detected. Yeah. But then what you want to do with this, you want to do functionality. So you want to judge, okay, what are these traffic participants doing? I detect those vehicles in the image space, but what they are doing, are they trying to overtake me? I'm approaching them. What is their velocity? What should I control my vehicle? Should I accelerate? Should I reduce the velocity? What should I do as an automated driving car? So for this reason, actually, you would like to have some points on that vehicles to actually know something about that, know those points where are located in the space. So okay, but what is the space then? You have to decide actually what is your geometric space, and then we attach a coordinate system which you can see now attached to the camera. So the camera, it's the main point of the world, and you have the overall coordinate system. So then we can define those points as being some 3D points in some coordinates x, y, z, describing where the point is actually. Yeah. So then, if we would like, if we know this, we can then judge. Okay, this position is here, and then is moving further. So then we can derive velocities. We can define. Okay, we should brake or we should not brake the vehicle. We should steer the vehicle or not. So that's something that we want to do. But how? And what's the relation of this image that you can see? And obviously you process by deep learning techniques, you have detections, but then how you derive the XYZ for the points. So for understanding this, we go to the pinhole camera model and this a bit discuss what is this pinhole. So imagine you have an object being this blue heart here now on the left, and you have a wall only with a very tiny small gap in it. So only one side ray can pass in only one direction, which means on the opposite side, as you maybe remember from biology, an image is formed but in reverse mode, as in our eyes. So there is the heart upside down. Yeah. Now, how can we mathematically model this? So if you go further, you can see this imaginary axis, the intersection of those representing the small hole that we have in the wall above. So then we have the projection point, projection plane, which is the image plane where we form the actual reverted image. And then you have a 3D point. Yeah, and how you create the projection, you draw the line from the 3D point through the camera small hole, so the camera center as we call it, and then we obtain the intersection with the plane. So that's our projected pixel of the 3D. But what is this 3D? We said previously that we have to associate a coordinate system. So then we have associated with the camera center a coordinate system, which means our actual point has coordinates. So is an XYZ point, which is projected by connecting the point with the camera center O in the slide. So then let's think about what if we move that plane forward virtually with the same distance called f. We will see what f means. That means that as our eyes actually are sending the information that we see reverted to the brain, and it's again reverted, so you see normal. You don't see upside down with your eyes. Exactly like this, our sensor actually reverts the image for us. So we will see in the end a normal oriented image. But this means if you move the plane in front virtually by F, you obtain a new projection, which is the new red dot, which is actually in normal orientation, not reverted. So we can use this further away to discuss. So we will consider that point to be our pixel. Yeah. So then let's simplify a bit the view. So we will consider this as our model. So same, we just reverted the image to be normal oriented. If you take the point in 3D, XYZ, and you connect that point with the camera center O, yeah, you intersect the plane, and that is your pixel projection. We do that by knowing exactly the f, which is a constant factor for the camera, meaning the focal length, and some camera intrinsics, which is the center of the image, the principal point. Now we can define this as a more simple problem. Let's think about this not in 3D, but in 2D. So twice the 2D means 3D. So we can see how this looks like if you look in the bird's eye view, so-called, meaning from above or from lateral view. We will discuss more about the lateral view is more somehow intuitive. So in the lateral view, you can see you have a point YZ this time because the X is in the different direction. We don't talk about X. And if you connect that with O, which is the camera center, in the end, you end up in having your pixel by intersecting the plane in the V direction, as you can see there. But now let's think about the vice versa. What if you have the pixel? Because in the beginning, we had actually the actual image itself. So by connecting the camera center O and the pixel, so the reverse problem, so the O there and the red dot on the image plane, you have the sight ray. So you have the direction from where originally the point was located in 3D. And then not by mistake, the sight ray there in the image goes through the red dot, because actually in the reverse problem, if you connect O and the pixel projection, you cannot recover the 3D points. So you missed that information. You don't know where in that sight ray actually the point was originally. But you know the sight ray at least. So this is the mathematical model behind an image formation. Yeah. So you can have a point, you can project it, you have the pixel. Vice versa, if you have the pixel, you can connect it with the camera center and you have the sight ray, not the point anymore. So now let's keep this in mind and see what's going on. If we go again back to our scenario, so what we wanted to do actually, we wanted to derive where those points are in the space. And now I slightly modify the red sight ray that you can see here. It goes a bit below the target vehicle because actually you have that point from the image, from the deep learning technique detection. You have the sight ray as we learned before, but you don't know where along that sight ray the point will be. So we have to somehow find out a solution to that to actually determine where the XYZ point is. So then let's think about. So simplify a bit the drawing, think about again. So I said in the beginning, you also detect lane markings. Yeah, of course, because you want to know where the lanes are. You want to drive the vehicle in the lane. So if we take those lane markings and we somehow use those to extend to the center of the image, an interesting geometric phenomena happens. So you can see that there you have a point where actually all the lane markings are intersecting each other. This is an interesting geometric fact. If you do an elongation of each lane marking detection, all together reach the same point. And that point actually we call it vanishing point. So it's a point where everything comes from or everything goes through. You can imagine when you drive on a night scene, you as a person, and it's very snowy outside, you have a lot of snowflakes coming around, and if you drive with the beams on, you can see everything coming from the same point. Yeah, and it's exactly like we have here. Everything comes from the same vanishing point. And that is located specifically on a line in image, which we call actually the horizon line. So it's the infinity for our image. Yeah. And everything is generated, remember, by just elongating the lane markings. And what is this in relation with what we discussed previously? So that vanishing point actually corresponds to a pixel position, yeah, in our lateral view above the image. And what that means, you can connect, as we saw before, the camera center with the pixel position and obtain a direction, a sight ray. So that's the little purple arrow that I sketched there. Okay, but what about this direction? This direction has a very interesting property. So if we take from the road any direction on the lane markings, which remember, those are parallel in the real world. So all the lane markings are parallel in 3D space in the real world. Those directions, if you see from lateral view, you can see a draw there on the red, on the green line representing the road. So you have those directions. And now you can see the relation in between any parallel line on the road and the actual vanishing point. So the vanishing point created for us a direction, and then we have any other parallel lines on the road sketched there with purple arrows. Yeah. And what we can see, they are parallel. That's a very important fact. So the property of the vanishing point direction, it's parallel to anything on the road plane. That means it's also perpendicular to the local surface normal. Yeah, so you have that n vector, which is the surface normal for the road plane. What this means, it means that by knowing the vanishing point, doing this geometric trick, we actually end up in knowing the normal vector to the road plane, which means we know the plane. Yeah. So by knowing the vanishing point, we detected where the plane is and what is the camera orientation with respect to the ground. Now let's imagine another situation. So let's go back. Let's see the vehicle. So the vehicle pitches up a bit. So imagine you have much more stuff in your luggage compartment. And then you have, again, the same logic. You have the lane detections. You now have a different set of vectors, which gives you another vanishing point, yeah, which creates another pixel. And now if you connect, again, the camera center with the pixel, you will obtain another direction, which gives you another normal vector. So for another situation, when the camera pitches up, you have basically a different orientation with respect to the road. So you redetect the road by using, again, the same geometric trick. So in the end, we can consider that this vanishing point based geometric view of the lane markings gives us the road plane. Yeah. So that's a very interesting geometric trick that we just done. So we can consider that we have a road surface estimation via the vanishing point. Okay, now how we use this? So let's go back to our original problem. Yeah. So we had a scene, we had some traffic in front of us. We detected that traffic via the deep learning techniques. And then actually we were discussing about this point. So our point originally was, okay, we want to have some information where those points are located in front of our camera. And why is that? Because we want to be able to judge if it's overtaking us, if we approach them, if we have to brake, if we have to steer. Yeah, so we have to do this kind of scene understanding, how it's called, actually understanding what other traffic participants are doing with respect to us. And for that, we need some 3D information. So now let's see what means we have that point in the image. It means if you connect the point, which is the pixel, with the geometric center of the camera, you obtain the sight ray as we defined it. The sight ray meaning the direction from where the information originally came. But now we don't know where in the space, actually, where is that point alongside the sight ray. Yeah? That was our original ambiguity. So you can see in the lateral view, above the picture, that the red dot alongside the sight ray, okay, we want to have that point which intersects actually the vehicle, but we don't know. We have to do something. Now remember what trick we did already. So we did the trick that we know the vanishing point, we obtain the surface. So now we know, in addition, the surface plane and how this looks like. Let's jump into the next point. So now you know the surface, the green surface, by knowing the normal vector n. And what we obtain now, we obtained actually in this lateral view, actually two directions. So we have one direction, which represents our original detection sight ray, meaning the vehicle in front of us. And then we have the surface. And now you can see that the surface actually intersects the original site ray, which means it defines a point. So by intersecting the surface with our site ray, we can derive that point, the 3D point. Because now we don't have the ambiguity where is on the site ray the point, because we intersect two directions, two lines, which gives us a point. Yeah, correct? So then we end up in actually knowing the XYZ point. And now we can do our scene understanding better, because now we know, deep learning part tells us, okay, there is a vehicle. Okay, but if there is a vehicle, where is that vehicle in space with respect to me? I can do the vanishing point computation. I will find out the surface. I will intersect the site ray that I have to the detection using my pinhole model with the surface. And what I get is the 3D position of the vehicle. So then by looking in time, how this 3D position is detected in this frame, in the next consecutive frame, in the next one, I can see how the object, the target object, so the vehicle in front of me or the one in the neighborhood lane is behaving. And by analyzing his position with respect to me, I can understand as an automated driving vehicle if I'm approaching them, if I'm somehow being overtaken by them, if they try to merge in my lane. So then knowing their behavior in the 3D space, how they moves, I can understand if myself as a vehicle, I have to brake, I can do an evasive steering, I have to do a bit of acceleration. So imagine you have in adaptive cruise control mode a vehicle, and then you have to you approach a vehicle, then your automated driving vehicle should detect, okay, I'm approaching something which goes slower than me, I have to brake a bit. So now I can do everything like this because I know the 3D position by knowing that trick with the vanishing point geometry. So actually, this simple trick, yeah, so starting from the lanes, intersecting them, having a vanishing point, understanding the scene in terms of road surface, and intersecting gives me the real missing part, 3D information of the pixel. So this simple geometry trick actually solves the problem of scene understanding that we had in the beginning. Yeah, so that was about our introduction in geometric computer vision. Thank you very much for listening. I have some time for answering questions. This is why I reserved a bit of time for you to really ask questions if you have any. Video, we can't hear you. You are on mute, I think.
Yes.
Yeah, now it's working.
Okay. Yeah, thank you very much for the presentation. I think it was great, and finally, we can actually use it for even for kids to demonstrate them why the geometry is good, for example.
Yep.
And but I wanted to ask you, in which situations is this working? I mean, it's working mainly for highways, or it's working also for other kind of for regular roads? How did you test the theoretical part?
So it's running, it's working actually in the situations where you really can detect the lane markings. Yeah, because that's the assumption that we made in the beginning. We have lane markings and you have to track them to the infinity to see how the vanishing point it is created. If you are in some roads where you don't have very reliable lane markings, that will be the limitation of this geometric approach that we described. And actually, to really see how we can solve in a better way this problem, we will have some next presentation in our next talks that we will have later this year and next year. Yeah, so that will be the more advanced solution. Yeah, indeed, you spotted that.
Okay, and yeah, just before continuing, I want to remind our spectators they can write, they can write questions even in the stream event page, or they can write them on the Facebook, YouTube, or LinkedIn where we are doing the streaming. So we have a question from Mihai Souca. So is there a competition between pure mathematical models and machine learning algorithms to solve the automated driving challenge, or do we need them both?
So
If it's so, the question is between,
yeah,
what
yeah.
do you choose, or if there's a competition between mathematical or AI? So how do you see this?
So on short, in the end, we need both. What is actually what can see as a competition, if you really want to call it like this, it's the fact that in the beginning there was no deep learning, no machine learning. Yeah, we did everything by handcrafted algorithms. Now, as the deep learning techniques went better and better, yeah, we start replacing parts of the original classic based algorithm with our deep learning. But there's not a competition. We just figured out how to do it better. But in the end, you cannot replace everything. You still need some geometric information to do automated driving.
Okay, totally agree. So it's a nice hybrid, I think, at the
Yeah,
end.
yeah. In the end, it's a hybrid. Now we replace more and more points. Yeah.
Great. Okay, so thank you very much, Ovidiu. And yeah, let's go to our next speaker.
Yeah.
Bye.
Sure.
Okay, and our next speaker is Lucian. Hi, Lucian. How are you?
Oh, hi. I hope you can actually hear me and see me.
Okay, so Lucian, the stage is yours. We'll talk after. Okay.
So, hello everybody. My name is Lucian, and today, as Ovidiu hinted, I will actually give you some insights into what we do for the deep learning part of automated driving. Maybe as a short introduction about me, I'm currently team leader for the machine learning team of our computer vision department here in the engineering center. I've been in Bosch for, I think, 5 or 6 years now, and I'm also pursuing a doctor's degree at the moment on the same topic of machine learning, AI, deep learning, and everything related to that. But that's enough about me. So let's see the agenda for today, what I want to. So, like I said, we will have some first insights into what deep learning is and how we apply deep learning for automated driving. Then you will briefly see exactly what topics or what tasks we solve using deep learning. You will see how we develop such algorithms using what we call a data-driven development, which is slightly different from the normal software development. And last but not least, you will see the main challenges that we encounter when we are. So without further ado, let's start with an insight to deep learning. So what deep learning is it but actually a branch of machine learning. So to first understand what deep learning is, we must first understand what machine learning is. So what machine learning does is it estimates an unknown function or a correlation between a certain input, in our case, the input is an image, and a certain output. Now, for this very simple example, let's say that the input image is an image captured by the camera inside the vehicle, which sees the road ahead, like Ovidiu has shown before. But let's say that this time the output wants to be a classification of the road. So we want to say whether the road is covered by snow, like we're in winter, if the road is wet or it's dry, right? I mean, we expect any driver and any autonomous system to change its behavior depending on whether it's snow, wet, or dry. The more snow and wet it is, the slower you drive, right? So then it's an interesting thing. So what we want to do is we want to estimate the function which takes as input the input image and then tells you what class it is. So you can imagine it's quite a complex function. And what deep learning does is it offers a solution for estimating such a complex function. And it does so by means of what we call artificial neurons. What's an artificial neuron? It's a concept actually inspired by what we have or what we think we have in our heads here. So basically, a neuron is an entity which takes several inputs, the yellow part that you see there, combines these inputs, assigns a weight to each input, and then makes a decision based on these inputs. Now, in our case, the inputs will actually be pixels from that image. So in a very simplified manner, you can imagine that the neurons are connected to the pixels in the image, And then what we want to do is we want to predict whether the pixels that have been seen actually contain a snow scenario, wet scenario, or a dry scenario. So it basically the state of the road, right? So this is what deep learning basically is. So let's take a deeper look then. I shown there that with one neuron, we can connect, for instance, 3 pixels there in a certain region. Now let's zoom in a bit in that region. Now you can imagine that if we randomly select 3 pixels to look at, some of them might be darker pixels, some of them might be brighter pixels. And probably the expectation is that the more white pixels you have, the closer you are to having a snow output, right? But as you already probably have imagined, it's not enough to just take a look at a few pixels because the image is composed by quite a lot. And then your decision must be much more complex. It's not enough to just look at a few of those. And so the question then is which pixels or which patterns represent snow, which represent a wet case or when you see water, and which represent a dry. So like I said, we don't want to just take a look at a few of them, but we want to take a look at many of them or all the pixels if possible. And then you can imagine we can't use a single neuron, but we use what's called a neural network. So it's a combination of neurons where each of the neurons looks at some pixels in the image and then passes the output to another layer of neurons, and each of them can make a small decision. Like each of them can say, hey, do you think I've seen here some snow? Yes, maybe no. Do you think I've seen some patches of water? Maybe yes, maybe not. If you combine a lot of small neurons like these, and each of them can do a small decision, can estimate a very simple function, a very simple nonlinear function, and you combine them together, then you can estimate a much bigger and much more complex function, such as f of image equals road plus, right? So then in the end, by combining a lot of such neurons, we can actually predict what we see in a certain image. So we estimate that complicated function. Now, Ovidiu was already hinting, and the question was, why should we do it with deep learning? Why can't we just estimate that function manually? Why can't I just write it out of my head? Well, because we have a very large input variety. So imagine this has to work in all situations. So it has to work for snowy roads, it has to work for dry roads, it has to work for wet roads. And for other stuff that might happen in the real world, like broken roads. I think this one is from some Eastern European country, which we know very well that the roads here are not so good. Yeah? Or if you imagine a wet road, it could be during the night with a lot of reflection. So imagine the possibilities of the input are very, very large. So you need your algorithm to cope with a very wide variety of input images. And you might look at these and you might say, okay, but it's easy. I mean, me as a human, I can look at the images and I can directly see what they are. Yes, because we already have a pre-trained, very powerful neural network right here. But for the computers, it's not so easy. They see the images as just matrices of numbers, right? So the pixel intensities that represent the image. So if I would show you these 5 images like I've shown them here, would you be able to tell so easily which is dry, which is wet, and which is snow? Probably not. So then this is basically where deep learning helps. It helps you estimate which pixel patterns represent different types of objects or different types of classes in the image. And of course, this learning is done by means of neurons, and it's currently state of the art in terms of image understanding. So if you want to understand the semantics, that is what you see in an image, currently for most problems, there is no better way to do it than deep learning. These deep learning algorithms have popped up very recently. So in the last 10 years, they gained a lot of popularity. The concepts were available since, I think, the 1970s, but we lacked computing power to actually train algorithms such as this. And now with the rise of supercomputers and every possible architecture of CPUs and GPUs, these concepts became a reality. And in the last 10 years, deep learning gained a huge popularity. And now it's state of the art. That's why us, Bosch, and I'm sure a lot of other companies also invest a lot of time into developing such as. So let's see how we learn with a CNN like this. So how do the neural networks learn something? Well, let's say you give it a set of examples, right? So a set of images which are with one of the classes that you want. You pass them through the CNN or the neural network, and then you get a predicted outcome. How we then learn is we check whether the prediction or what the algorithm thinks it saw in one image matches what a human says or an expert says was really in that image. And if there is an error, like a misprediction, we back propagate that error through the network of neurons, and we change the small decisions that each of the neural network, each of the neurons make. So let's take a concrete example. Let's say I take this simple snow image, I pass it through my neural network. So each of the neurons here will make very small decisions based on what they saw. And the combination of these decisions will tell us, let's say it's wet. Is it correct? It's not correct. It's wrong. So we can see that it's wrong. And we can then check where exactly it was doing wrong decisions, let's say. And if you look at my red highlighted lines there, it means we identified that the error came from these locations here. So we can adapt the decision such that next time the prediction is correct. Let's take another example. Let's say this time we show a dry road. We again pass it through the neural network. Then this time it predicts it's no. Again, it's wrong. Again, we check where it was wrong. We back propagate this through the so-called backpropagation algorithm. We change how the small neurons decide what they saw there. And we repeat this process with a lot of images and with a lot of examples until finally we have a good prediction. Like here, a wet image is correctly classified as. Of course, there are a lot of tricks and a lot more maths behind this, not just what I've shown here, but these are the basic principles on which it works. So now let's see what else do we do with deep learning. So you've seen an example where we just classified the entire scene into something. Let's say we classified it into the road's condition, if it's snowy, wet, or dry. We can also classify each pixel in the image into a certain semantic class. And this is what we call semantic segmentation. So here, what the neural network outputs is one semantic class for each pixel. So what you see here coded with red is the pixels which we identified as road, yellow as markings, blue as vehicles or pedestrians. And I think if you zoom in a bit, you will see also with purple the curbstones, for the edges of the sidewalk. Another interesting thing we do also with deep learning is detection of various object types. So here we don't want to classify the entire scene, neither do we want to classify individual pixels. We want to have bounding boxes which tell us where certain objects are. And the objects can be vehicles, they can be pedestrians, they can be road signs, they can be painted markings, any traffic lights, any objects of interest for an automated driving vehicle. And what we use it for. And so, like I think my colleague was hinting before me. So if you want actually an autonomous system or an automated system to take control of a vehicle, you want it to understand the scene completely. What does understand the scene completely mean? It means, if you look at the picture here, it means you want to know what the objects are. So you want to know that the thing on the left is a cyclist, the thing in the middle is a pedestrian, the thing on the right is a car with an open door, right? But you also want to know where they are. And for where they are, this is what Ovidiu has shown you before, that we also compute the the location of the objects or their 3D structure. And if you know what the objects are and where they are, then you can actually act. And what acting means, it means you can control the vehicle. Like, for instance, you can brake here for this crossing, right? Okay, but coming back to my original deep learning presentation. So I said in the beginning that the development of such algorithms is quite different from normal software development. And I wanted to show you how this goes. Why it's different? Why do we do different? The idea is everything is centered around data. Why? Because we always learn from data as opposed to conventional algorithms where you don't need data to learn from. You can just apply simple formulas and it works. You don't need to train it on thousands of images. So what do we do for this data-driven development? Well, basically, you can imagine we have our camera, of course, mounted inside the vehicle, and we just record a lot of data with this camera, and we compose what we call our raw frames. So we basically store all the image. Now, if I want to train a certain neural network for a certain problem, I want to take from these raw frames only those which are of interest to my problem. Let's say here I want to detect painted markings. For instance, arrows. I think everybody knows about directional arrows, right? They show you where you should go, which lane you should choose when you want to drive in a certain direction. So what I want to do for this is from the entire data that I have, I want to select frames where I have such painted markings, right? I'm not interested when we're driving on the countryside and we can't see any markings. Then what I want to do, of course, like I was hinting in the beginning, I have to label them because then I have to show the CNN, hey, when you see a marking like this, you should know it's a straight arrow. When you see a marking like this one, you should know it's a left arrow, and so on. So I want to label them. This is usually done manually or automatically. If it's done manually, then it's actually done by a person. Then I actually train my CNN. CNN actually stands for convolutional neural network. The basic principles are the same as what I showed. Well, this training is usually done offline on very powerful computers, GPUs mostly. And after it's trained, what we do is we deploy it in the vehicle. What does deploy in the vehicle mean? It means we actually make it run on the hardware that we have available there. So it runs in real time, and it can predict in real time where it sees painted markings in this case. Same ideas apply for this road type estimation. It applies for this semantic segmentation I've shown, and it applies for any other object detector that I've shown here. So it's quite a bit different from the normal or the conventional, I would say, software development. So what challenges do we have when we do this? Well, like I was saying before, we need everything to run in real time. What does running in real time mean? It means with several frames per second. Now, of course, how many frames per second? It depends on the problem. 10, 20, 50, 100, depends on the problem. The idea is it has to be real-time worthy. Real-time worthy meaning that if something happens in traffic, like you get a cyclist which is crossing in front of you very fast, or you get another car which crosses in front of you or brakes in front of you, you have to be able to react in real time, meaning all the algorithms that me and Ovidiu have shown have to work very fast. Otherwise, you will be very slow in reacting. And if you're slow in reacting, you will get very, very poor behavior. Then another challenge, of course, is having good performance in all scenarios, right? So this has to work in all the countries. It has to work in all daylight conditions, like during the day, during the night, during dusk and dawn. It has to work during different weather conditions and all of that. So that's also a challenge in itself. And of course, there's the challenge of making everything safety and process compliant and let's say go by the rules that are already defined. Now, I will focus on the first 2 points for today, as we already have, I think, a process and safety compliance presentation today. So we will take a peek, let's say, into the first two. And then if you stay tuned, I'm sure we will follow with some more insights in the next one. So what do we do for this real-time problem? We do a thing called multitask perception. What is multitask perception? So what you've seen before, up to what I've shown now, is I've said you have an input image. Yeah, you have a certain neural network which gives you a certain output, and this output can be either a class for the entire image, a class per pixel, like for semantic segmentation, or an object. All right. So this means if I want to detect 3 types of objects, maybe do a semantic segmentation and then do 3 scene classifiers, I need a lot of CNNs to run. And I want all of them to run in real time. This is quite expensive. So then the optimization that we do is basically we run a single CNN or a single neural network, which has many outputs. And all the outputs are computed together in the same time. So I call them here tasks. You can imagine these tasks as being everything we discussed before. Object detection, semantic segmentation, classifiers, anything. So to make it clear, why is it really better to do it like this? Well, like I said, if you do it as multitask, you have a single network with more outputs. Whereas if you create one algorithm for one neural network for each of the tasks, then you have 4 neural networks. And then you can imagine, of course, this will require much more computations, meaning it will require much more runtime in the system, meaning you will react slower. And it will also mean you will consume more power. And it will also mean that the device that's in the vehicle will generate more heat. And all of this is, of course, undesirable for any automaker, right? Of course, there are many other optimizations that we do, but this was, I would say, the one which is mostly in trend with the recent advancements in literature. And then as a final interesting point for today from me, the second problem I mentioned, so the performance problem. Now, of course, if you have not ideal performance, there's a lot of stuff you can do. You can play around with your algorithm, which is something we obviously do, and probably we will discuss this in one of the next sessions. But the other interesting thing you can do is you can play around with the data that you have. So the challenge for any machine learning algorithm is finding the right data for your problem. And people usually think, yeah, I spent 10% of the time gathering the data and 90% on tweaking the algorithm. It's not. It's actually the other way around. You spend much more time on finding and labeling the correct data rather than tweaking your algorithm. So why? Why is that? Well, imagine, like I've shown before, each data sample that we use has to be labeled. And if you want the label to be very, very good, you have to do it via a human. So somebody has to, if we're talking, for instance, about semantic segmentation, somebody has to label each pixel individually and say, here you had a car, here you had a vehicle, here you had a pedestrian, here you had a truck, here you had the road marking, and you can imagine it takes some minutes just to do one image. And of course, it takes time, and of course, it's also expensive. So then the challenge is to only label relevant data, because if you only label relevant data, then you are not spending money and time on labeling what's not necessary. So as an example, take, for instance, these 2 images here. Now, in these 2 images here, they are very, very similar to each other, right? So it doesn't really make sense that we label both of them, only one. There's a more in-depth presentation from me and one of my colleagues, Ariton. I think it was called From Big Data to Knowledge. Unfortunately, I think it's in Romanian, De la date la cunoaștere. So if you're interested, you can also search for that on these online platforms that we're streaming on, and I'm sure you can find it, and we'll have more insights on that presentation. Another interesting thing about data is not only identifying cases where similar data is not needed, but finding corner cases. So remember, like I've shown in a few slides before, If we're talking about wet roads, maybe we want to see wet roads during the day and during the night. If you're talking about dry roads, maybe you want to see dry roads with cracks in them, or snow roads with cracks in them, or any kind of combination such as this one. So you want to search for all the possible cases that can appear in the real world and identify them. And of course, ideally, we would like to do this without any human intervention, because if I need human intervention, then somebody has to browse through millions of images and select them, right? So let's say we want to search for examples such as this one. We don't want to spend effort for somebody to actually search for limit cases such as this one. We want to find them automatically. And we have ways of using the algorithms themselves of finding such corner cases. And these methods are usually based on where the algorithm is unsure of itself, similar to how a human might be unsure of himself when he tries to predict what he sees in an image, or they might be what we call entropy-based, or when we run multiple algorithms on the same images and we check where their predictions disagree. Similar to if I would ask 5 people what they see in a certain image, and if their answers are different, it probably means there's something weird there. Yeah. And I think that's all I wanted to present for today. I hope it helped. I hope you learned something today. And if you have questions for me, of course, I'm open to one.
Thank you, Lucian. Was a very good presentation, and will clarify me, at least for myself, how you do all these pattern recognitions. We have a question from Andy B on the YouTube chat. So the question is Bosch also designing their own systems for training, like GPU AI or hardware accelerator, or are these provided by some other vendor?
So the question is about the hardware that we use for training, or the hardware that we use for actually deploying in the vehicle?
For training.
So for training, we don't design our own GPUs. We usually use what's existing on the market. So Bosch doesn't design GPUs or CPUs.
Agree. What about the production? So for applying them and do the machine learning on real time?
So in real time, that's unfortunately confidential, so I can't give a lot of details there. But what I can say is we use accelerators which are specifically designed to run our algorithm.
Oh, okay, nice. Yeah, this is what actually I wanted to ask you this too. So you have some specific hardware to run your
yes.
And when you design all these algorithms, are you thinking also to the hardware stuff layer, or you have constraints?
Of course,
right.
Yes. Okay. So when we design any algorithm, not just deep learning, we have to think about what hardware we can actually deploy it on. This was what I call the real-time problem. That's why I gave an example with that multitask perception. But we also do it the other way around. So when we design or we search for a hardware that we want to use, regardless of whether it's designed by us or it's designed by somebody else, it doesn't matter. We check what we need that hardware to be able to do, such that we can run on our algorithms. So it goes both ways.
I see. Okay, great. Thank you very much, Lucian. And now let's go to the next presentation, where we'll talk with Stefan. Stefan, if you can hear us. Okay, hi, Stefan.
Hello, Ovidiu.
Nice to see you. The stage is yours, and we'll talk after.
Perfect, thank you. So just a few words about me. My name is Stefan Daraban. I'm the technical leader on virtualization topics in the Bosch Automotive steering department here in Cluj. And I'm also responsible for virtualization in the complete division of Bosch Automotive steering. So today, what I'll do, I'll present this topic of virtualization, not like a training, because it's not enough time to present such a complex topic, but more to raise awareness of what's coming next in the automotive industry. So, for example, we even have discussions, we as Bosch, with customers that they say no virtual ECU means no ECU. This means that in the next years, when the virtual ECU will be standardized, if a company will not be able to deliver a seal model, a virtual ECU, there will be no longer a business, and there will be no request for the supplier or that company to produce software or a ECU for that customer. Okay, it's rather new, this platform, for me. So, okay, so I'll just start to present only this trend. I'll also present some use cases. For example, there are customers, exclusive customers that produce around only a few thousand models per year, or 10,000 of models per year vehicles. And for them, a prototype really costs a lot. So the trend is that all their new concepts, all their ECUs will be transferred in the virtual world. For example, video system, braking, steering, powertrain. They will transfer it in a virtual world, and only when they realize, okay, my network communication is complete, also my main functionalities are working according to the dynamic of the vehicle that we want to have, only then we'll be able to order to the customers, to the suppliers, the ECU that we want. So there is a big trend that everything will be developed in virtual world, and then only when the solution is complete, they will transfer it to real world. So in this way, they are able to detect inconsistencies in their design. For example, functionalities for highly automated driving. Also, they are able to start working on their functionalities development before they have the hardware. So now I think most of the people that work with hardware, they see this problem of semiconductor crisis, that we are no longer able to get all the time the prototypes in time, and also this imposes a big problem to the development of software. Also, this kind of product will also, so the virtual ECU will also be useful, for example, to get fast feedback of the software quality. So developer does his implementation, and after a few minutes, he also has a report where it shows that his implementation didn't break when the software was integrated, doesn't break other functionalities that were interacting with this component. And now the newly developed feature is not a bug. Also, another big advantage that extends the limit of software is, for example, extends the limit of testing software, is that we are able to inject errors at hardware and system level that in normal way, if we would do this on the hill, it would destroy some of the components. And in this way, we can really stress our software and really see that we can improve our software development process. Another thing is a cost reduction. So, for example, imagine that our hills cost more than 100,000 euros. So these seals are harder in the loop. This means that we need some big systems that allow us to test our steering gears, steering power packs, and imagine that we also need the laboratory that needs special equipment. Also, the electrical network needs to be arranged in such a way that we have these power consumption tools, and definitely this costs a lot. And with our virtual ECUs, we are able to use some software licenses that cost around 15% of the cost of a Hill system. So summing up all the disadvantages that the real system impose, imagine the cost reduction that we could have if we move to the virtual world. And also, as I previously mentioned, we have this use case where some customers already in the automotive industry already start to move their design development in the virtual world and not in the real world. So that's why we need also interconnections between ECUs in order to allow a steering system to communicate with the video system, with the braking system. In this way, you can implement highly automative and autonomous driving algorithms. Okay, so there are four main components that you really need to have in order to virtualize. But let's begin with something simple. What is virtual ECU? Short answer would be that any functionality that can be executed without having hardware. But in fact, we need these four main components. So we need to have our hardware virtualized. This means we need to have some plant models that need to be simulated, actuators, sensors, mechanical steering gear in our case for Bosch Automotive steering. Also, what is very important is this communication bus in order to allow different virtual ECUs to communicate to one another. And also we need storage. So for example, imagine that we would like to simulate a reset of the virtual ECU. And in order to do this, we need to emulate non-volatile memory. For example, data flash or for example, EPROM also. And when you do a reset, you also need to do a blank check or to erase your RAM in order to be able to restart to the initial conditions. And for this, you need this virtual storage memory. And another topic that Bosch is working at the moment is virtualization of the operating system. So we have these tools that usually when we do system release, we measure how the tasks are executed, when they are executed, and you can get out some reports, some configuration files out of this tooling, and these configuration files can be imported in the virtual ECU. So in the end, your virtual ECU will have the same timing like it has the real ECU. Okay, so also it's very important to present the types of virtualization that we currently have in the automotive industry. So we have type 1 that basically you just have all your software application layer where you inject data basically, and then you check your output. So basically, this is just to test your application software, how it reacts to inputs. This is the fastest one, but also it doesn't really give you overview how the complete functionality would behave. Then you have the possibility to introduce also mechatronics model, sensor model, where and also your application software. Now your virtual ECU is able to interact with other virtual ECUs through signal-based. So you also have some part of your basic software. This is also one type of virtual ECU that is requested by some customers. And then now we are coming to the most interesting part. So we have type 3, which basically here it also introduces all the parts that I have presented earlier. So the time modeling, where we'll be able to have an OS very similar with what we have on the target, the plant models, application, the part with the storage. So we have data storage. So we also have most of the basic software. And also the communication bus. So in this type of virtual ECU, now we are communicating through messages, through protocols that are used in the automotive industry, CAN, FlexRay, Ethernet. So this part is also what we have currently under development in Bosch Automotive Steering. This is based on, this is basically our platform. Then the latest one is type 4. This one has uses the same code that you have on the target. So out of the build environment, you get an hex file, and this hex file is included in a virtual ECU in a simulator that it's able to interpret the machine code. It's rather slow, but gives you really exact behavior of how your software is behaving. And in Bosch, we have two main virtual ECUs that we really invest our attention. So one is type 3. Is the platform that is also under development in Bosch Automotive Steering. What I didn't mention up until now is that Bosch, as entity, it's leading this topic for standardization in the automotive industry. So he's leading the consortium where also important tool vendors are part of it. Important OEMs and also other important suppliers. And then we also have this virtual hardware. So that it's able to use the hex file as we have it on the target. We'll also use it in this simulator that can run under Linux or under Windows. The main difference between when using one or the other is the use cases. So for example, if we would like to simulate an autonomous driving system, how it behaves and how it reacts to certain inputs, we would use the virtual ECU type 3. But if we really want to concentrate on developing an ECU without any target, we will definitely concentrate to use the virtual hardware. What I'd like to present now is a basic setup that we'll definitely encounter in the future. So whenever a developer will want to do some changes, we'll start first the development, we'll start first to test it on a virtual ECU. And when he finishes the implementation, it will merge his changes. Then a tester, or not only a tester, but will have these pipelines that will start automatic tests with the newest changes. And the developer, the manager, the tester will have reports that will show how the new implementation or the new feature is behaving. In order to do this, we need a proper process that will allow developers and testers to use a virtual ECU methodologies, because they need to know how to do this, and the proper tooling. And here I have put two keywords. I don't know how well they can be seen. So one is security, and the other one is qualified. So what does this mean? So imagine that a virtual ECU will be like an archive where you'll have some dynamic libraries or some binary files that it may be the data flash, and also some mapping of inputs and outputs. So this kind of format can be corrupted. So definitely we need, and also this is under development, that we have security when virtual ECU is transferred to the customer, when the virtual ECU runs. So besides the security that we have inside the ECU, that one will also be present in the virtual ECU, but we need to add additional security just to make sure that we conserve the data integrity of our delivery. Then another important point is qualification. So we need to have a process that will allow the project to perform virtualized releases. What does this mean? It means that the safety standard now allows to have only QM tests to run on virtual ECU, and Bosch is now able to run even ASIL-B. So with the proper process, we'll be able to run ASIL-B up to ASIL-B components in a virtual environment. In the next release of the safety standard, there will be some exception that will allow or will introduce the topic of virtualization that can be used to test even ASIL components. Okay, so I would also like to present so this was a general overview of what virtual ECU means. I only summarized the topic of testing, but there are also some key points where virtual ECU is used currently in the new features that are implemented for autonomous driving. There are some ongoing patents that were done even in my current team, but I will leave this for the next meetings. And now I would like to present what we are currently doing in Bosch Automotive Steering. So first of all, it's very important to see the vision that we have. So one key point for us is to reduce the time to market. This means that our product is getting more complex every year, and also the demand for the customer is to reduce development time. So imagine that if we do not come up with new tooling and new methods, definitely we will not be able to withstand the pressure that we have from our customer. And definitely the virtual ECU can help us to implement our code without, for example, without having the hardware yet available. Then also, we as Bosch Automotive Steering want to deliver a virtual ECU to any customer at any time. This means that we need to have our virtual ECU ready at the same time with the target software. Otherwise, it doesn't make sense to deliver a virtual ECU. So if we develop a target software and then we make a virtual ECU after 1 month or 2 months, it doesn't really make sense because everyone would like to use the target and not the virtual ECU. So that's why we need to be prepared with methods and tooling that will allow us to have the virtual ECU at the same time with the target. Also, we improve our process in order to be able to have the virtualized releases. This means that we want to reduce our hill capacity, that we are able to create tests directly in a virtual environment and test them on the hills. And not test them on the hill and test them directly in the seal environment. This is one key point. Then we also want to improve the process that will be able to do virtualized releases for ASIL components. And also, very important is to have fast feedback of the software quality. So this means that with every implementation that a developer does, there should run in the background after merge. There should run in the background some tests that will show that the newly integrated component does not affect other existing components that were previously working. Okay. Here, this is the current status that we have for our virtual ECU. I hope you can see here the legend that I have put. So somehow, if you see red, doesn't really mean bad thing. I just chose these colors so it looks rather nice. So whatever you see with this yellow color, it means that we have the target. We have the target code without any changes. I have mapped all of the points that I will explain regarding virtualization on an AutoSAR architecture, and also describes the complete system. So we have our microcontroller plus an infrastructure layer here where we simulate some behavior of the microcontroller. And on the lower part here, we have the plant models. So yellow, like I previously mentioned, is target code that doesn't have any changes. Then with this reddish color, it shows virtualized components that perform the same behavior like on the target. For example, communication drivers. Here we replace the part that data is exchanged with the outside world of the microcontroller. Here we basically connect to a virtual bus where it can be interconnected to other virtual ECU and exchange messages. So here we have the complete communication stack. Or for memory drivers, we are able to save data in binary files that after a reset, the data flash can be read and the virtual ECU can restart its normal operating mode. And we also have another type of virtualization where we have this pink color, where this functionality just allows a request from the upper layers not to return an error whenever they are accessed. So these crypto drivers, we are currently under virtualization process. So this point will certainly be covered in the near future. But currently it's just stopped, so we make sure that a request will not produce an error that will generate further some errors in the error memory. Okay, so I would also present one example So here, for example, we have the end stop functionality. We have a comparison between our hill result and our seal result. The same test that we run on hill, we run them also on seal without any changes. And I have put here some waveforms. It can be seen that they are pretty similar. So the main thing is that whenever we'll do the qualification of the virtual ECU, this is a key factor that we do back-to-back testing between the waveforms from hill and the waveforms from seal. So this and some functionality basically is able to prevent damages of the steering system when it tries to move to the maximum, to the extremes of a rack position. So whenever you steer to the maximum, usually you have some mechanical components that prevent the steering gear to be damaged. And maybe you heard this time that software can replace hardware, but in this case also software can replace mechanical parts that we can detect in software when we reach the almost maximum endpoint, and we'll do a counter force in order to prevent the damage of the steering gear. And this is what the test does. It tries to learn those maximum endpoints. So thank you for your time, and certainly I will come in next session when I can even present more results. So if you have further questions, please.
Thank you, Stefan. I think it was a great presentation, and I didn't know, at least myself, that you can digitalize so good the ECU. Can you can provide different versions anytime to a car manufacturer, right? And I mean, you can upgrade any ECU you already have with a new one, or it's then put in the hardware and but there.
So our deliveries to the customer are like this. At this moment, we also deliver the target, the product itself that goes in the vehicle, but we also deliver the seal model. Like I mentioned, all these seal models are used for autonomous driving, because renting a track is very expensive, and you have this steering product, you have the braking, you have the powertrain, camera, radar, and so on, and you don't have let's say the proper condition all the time. For example, you do not have pedestrians that would like to throw them in front of the vehicle, and so you simulate this, and in this way you can train your algorithms. So that's why these seal models are really useful for them. One thing to train and to implement the autonomous driving algorithms, and also to improve your dynamic of the vehicle.
I see. Okay. And what about digital twins? Can you put can you create a digital car at the end?
Yes. So like I mentioned, I only illustrated the topic for testing, but definitely this is one part that is really interesting, that will have digital twins. This means that the virtual ECU either will run in the cloud or inside the vehicle at the same time with the actual system, and it will act like either as a supervisor, so it will be able to simulate or predict when you will need maintenance. This is just one of the examples.
Okay, and one more question. Having this virtual ECU, with how much time do you think you enables you to create better version and to have more releases? Because I think before you will have to try to create the hardware for testing and then test it in real world. But now if you have this virtual ECU, you can I think play way faster. So did you decrease the length of a release?
Us in the current business unit, not, because we only wanted to see if this concept is feasible for us.
Okay.
And now we reach promising results, and definitely now we allocate more budget, more resources, and the plan is to reduce our development cycle time.
Okay, and now we have a question from the YouTube. It's from Bondrik Nikolai, who's asking why on seal results the motor assistant graph has smaller spikes than in the hill results. There is any reason?
Yes, there are certain. There could be multiple reasons. So, first of all, it could be the sampling time. That, for example, this hill really is able to sample a lot faster than our virtual ECU. We can also improve our modeling to cover this point. Second point, there could be also components, parasitic components that we did not model in the virtual environment in our plant models. So this is also a second point that we would like to take a look on it.
I see. Okay. And with this, thank you very much, Stefan. Was really good information about virtual ECU. And now let's go next.
Thank you.
Thank you. Our next let's see if Andrei is online. Okay, so next presentation. Hi, Andrei. Can you hear us? Okay.
Yeah, can you hear me? Hi.
Okay, so I'm not sure who will start, you or Silviu, but let me know when you want to do the switch.
I'll start. You can put on the slide.
Okay, so we put the slide and the stage is yours.
Okay, hello everyone. My name is Andrei Crăciun, and together with my colleague Silviu, we'll try to show you some strategies that can be used for what we are calling training data selection. Let's see a little bit why, what is this process means and why it is needed. So whenever we are talking about machine learning algorithms, machine learning processes, machine learning strategies, we have generally some training data set which is labeled on top of which we everybody trains models, right? So if we see this in a pipeline, starting from a training data set, a training process will have a model as a result. Then the real data, which we are calling validation data, comes into place. And generally, we want to see how well our model is trained. So what happens? This model is run against this validation data, and we see some results. Of course, there is always place for improvement. So we need by each time we need all the time to add more data into the training data, label that data, and make sure we train the model over and over again. Now, of course, labeling from all of these processes, labeling is one of the most expensive one because it includes human interaction, and it's also expensive from the money point of view, but also from the time point of view. So when dealing with huge data sets, it's pretty hard to label all the data. So it's reasonable to think that an ideal process would be to select, to label only the relevant data and to be able to select that. What relevant data means data that would improve the model, right? So data that would add quality to the model. If we are thinking autonomous driving and the automotive in general, one important step is what we call the pre-processing. What that means? So this sometimes means normalization, sometimes it means I don't know, image resizing. So if we imagine we have models that have I don't know, that want to check what are the lanes, right? The lanes on a road, and a different model that wants to see the pedestrians, and the data the providers have given is in the form of Windows Media videos, right? As models are validated and trained, they may happen to be trained on pictures, on images, on JPEG images. It doesn't matter. So one pre-processing would be to extract those images, those image files from the video files and to feed it to the evaluation process. Why is this challenging? And especially with big data sets. This is challenging mainly because there may not be enough space, enough storage. So the validation and this with enough, by enough I mean sometimes physically, but sometimes it may cost. If we imagine, if you think of cloud-based storage solutions, then this the costs could increase very high if depending on what is the result of this pre-processing step. And usually sometimes there is a certain normalization needed because the models are trained specifically on very particular formats of images, if you are talking images. So this pre-processing step needs to be taken into consideration on all this training data selection process. If we are talking on where the action happens, so first of all we have the training and we have the evaluation. These processes involve usually high GPU processing. They need to be run on usually on clusters where we have this kind of GPU clusters where we have our GPU cards attached, and we have this processing power, and we don't necessarily need these one are not necessarily CPU intensive. So this means the infrastructure could be somehow specific. On the other hand, pre-processing and selection could happen, or it's natural to happen on CPU. And generally, if we think from the infrastructure point of view, these clusters, the CPU ones and GPU ones, sometimes are not the same. There are different topologies even involved sometimes, and sometimes what I'd call different infrastructure for, I don't know, if I'm thinking now of potential hybrid cloud approaches when some of the nodes involved are in on premises and some of them are on cloud solutions. So why is this important is that, as you may see here, there is this pipeline, a pipeline involved. So one or more pipelines involved, and there is a certain order that things happen. But if we keep also into consideration the the previous slide and the fact that the validation data may not be we may not have enough space, enough storage for the validation data, then this means that between pre-processing and labeling, we need to make sure what is kept, where it is kept, and how can we make this accessible. Last but not least, labeling involves human interaction. This means an operator, if we see this as a pipeline, it's an operator that runs on human power, to put it like that. This is it could be seen as simple, but it has a few complications. One of them would be like humans are not fast. Machines are pretty fast. We can expect they they work all the time. They work in parallel. Humans are not that fast. Humans work on time zones. Humans have a certain schedule, working schedule. So this means things like session. If we imagine session connections between these operators are not possible, because one session could be at the end of the at the end of the day, and then it takes, I don't know, 16 hours until next workday starts. So these things are not always possible. So somehow, when we are talking about this labeling process, if we want to integrate this in this automatic training process, now this is not does not play by the rules machines use. Okay, having this in mind, we are actually facing this all these scenarios, and next I'll try to show you how we just a few simple strategies how we are tackling, or how one can tackle this issues, because there are more of them. So first of all, we have 3 playgrounds. We have GPUs, CPUs areas, and humans. Now, GPUs or CPUs are machines, right? But we need to take care these the processes that needs to run on the GPU playground and on the CPU playground, because some are GPU intensive, some are CPU intensive. Why I separated these? Because of course there are solutions as it is. Kubernetes has options. Also, there are other solutions that can merge these two together. The orchestration part could separate between which processor runs on each resources. I've put this different in 2 different groups, because they sometimes play by different rules, especially because of the tools used. And it's better to see them as different things, deal with that, and if they come together, then it's even better. It's an advantage. It's a plus. But if we design our structure as if they would be our infrastructure as if they would be on the same cluster, then when it is the case that these are separated, we have this kind of issues. So we have 2 main ways of interconnecting between processes inside those 2 playgrounds. First of all, they need to have a common storage. This is important because usually we are talking about big amounts of data, and these big amounts of data involve storage expenses. So it's good. It's always better that all these places where processing can happen to have access to the same storage, right? To be able to load files, save results, this kind of stuff. Now, when we are talking about realizing the pipelines, of course, as you previously seen, not always this happened. The pipelines happened on the same playground, so there are kind of cross playgrounds. The easiest way we found to deal with that is having an asynchronous approach and having these communications done on message buses. And on message buses, we kind of find out that it's easier to send pointers to the data which is located in the storage, right? So simply, if we want to, I don't know, to run an inference on an image, we may send that the path of that image, and that to that path can be located as long as the next operator or next processor has access to that storage. When talking to humans, things change. Why? First of all, it may happen that there may be strategies like gamifications. You guys may seen that those the captchas we have around are a set of images where the user needs to check if it's a car or whatever is in there. This kind of what if that those images would be provided in a from this kind of storage where, I don't know, somebody makes a validation behind or a training behind or whatever. This may involve some security issues in giving access to those interfaces for the user, giving the access to those on the main storage. So the general strategy, or a good strategy that could be used, it's make a separate storage for each party that is handling labeling. It is sometimes it may happen that there are I don't know, some external team that is doing just the labeling, just receiving or labeling on some part of the data, and it's a good strategy to somehow make a if we imagine services, on services we have that DMZs, we can imagine having also the data on DMZs, and that data could be that data is only related to labeling. It's a limited set of data, and the labels are again added on that zone, and then that zone is synced by some firewalls, by some security levels with the main storage. One important thing is the user interface, and usually, as you guys may know, a label is generally a text file, different formats, which let's assume we have one that we have a model that detects pedestrians. Then we'd have an area marked by the coordinates. So one important thing is how these are made. If we have a simple tool that would help users to just circle with the mouse that area, then the labeling would be faster, and then by that less expensive, and more important, less expensive on time, because in a shorter amount of time we will be able to have more labels, and also the quality could be better. So this UI plays an important thing. Also, it's important to, when designing this kind of user interface, it's important to integrate these with the whole pipeline, because once one of these images or one piece of the data is available, then this data could already come into the game of the whole training. As I've talked here, this whole thing involves continuous that data gathering on the validation data set. Of course, it's important to have this data as fast as possible. And how can this be done on from a vehicle to the cloud? Architecture and strategies. I let Silviu tell you this story.
Okay, thank you. Yeah, hello everyone. I'm Silviu Cacoveanu, a colleague with Andrei. I'm mostly focused on connectivity, big data, and cloud development here in Bosch. So yes, as Andrei just mentioned, I'm gonna go over how we can get data from cars, large amounts of data, and make that data available for training. So here you can see the classic approach of doing this. So on a car, we've got several sensors gathering data. These can be radar or cameras. We can have speed information, for example. Some of those are going to be used in algorithms to try and gain some knowledge about the situation the car is in, based on models trained by developers and installed in cars. And all this data from sensors and the results from the models, they are all recorded on the test cars. And usually we are recording very large amounts of data, storing them on the hard disk on the car. We're talking about tens of gigabytes of data for just a single drive. And with this data, then we need to get access to this data. We need to move it into the cloud where developers, people that work on functions, on classifications, can actually use the data to improve their models, to perform new training, to develop new functions. Yeah, so such a large amount of data, it's not very easy to transfer it over the air, over a mobile network, for example, directly from the car. With the new developments now with 5G, for example, we may be coming close to that. But even with 5G, it's not available in a lot of places. So it's not, yeah, this is definitely not what's done with the classic approach. With the classic approach, the data is actually moved manually. The disks are moved into the cloud, copied into cloud storage where they become available for indexing and data selection and training steps. And then models themselves are also moved, installed manually in the car for new testing. Also, we are recording large amounts of data because we don't even know yet if all the data is going to be useful. But since this loop of getting the data out of the car and into the cloud and processing it takes such a long amount of time, the best approach is to record as much as possible, just in case you will need it later. Now, of course, this takes time. We're looking at ways of making all this process as faster, so as fast as possible, of course. So to go about that, there are some improvements we are working on making to this whole process. First of all, don't store everything. Just try to determine what relevant data may be for our process in the cloud and select that directly on the car. So that would reduce the amount of data we need to then move to the cloud. Then send the data over the network, this being a mobile network. So send that as soon as it becomes available. Then in the cloud, of course, we've got a smaller amount of data. What we hope is only the relevant data that we can index and make it available then as soon as possible for training new algorithms. So this whole approach would make the whole process faster and hopefully would allow developers to work faster on improving the functions and get feedback a lot quicker. So in order to do that, as I've already mentioned here, on the car itself, the change to the architecture is that we already have the sensors. We're running the classification, we get the result, but then we have this extra selection step, which will just identify what is relevant for a certain specific function, and this will depend between functions. So this step is also required to be configurable, adaptable to every specific function. Then this data is again stored on the car hard disk, but now we bring in new components that we can use to send the data to the cloud. So so here the example I'm showing is working actually with 3 components. These are all working in parallel. First, for sending data into a Kafka cloud. Then there is another for sending data into Azure storage. So everything here is with Azure, with the Azure cloud, and another one is just for uploading files directly into an Azure storage with which is prepared for data lake architecture. Yep, let me just move on forward. So this would be the actual sending process. So here, the 3 components that I'm presenting there, they've been designed to be pluggable. So we could use either of them, all of them. And they communicate with the cloud on different protocols. So Kafka has its own protocol. The others would work with Azure storage. So and they would usually go over HTTPS. At this step, besides the fact that we are working with different protocols to send the data, we also have implemented some strategies. So we need to be prepared for situations where, for example, the car loses connectivity to the network. We don't want to lose that data. So we've implemented strategies to retry to send the data, and also to try and maybe merge the data. So we're also looking at archiving, and this again will depend on the protocol, how large the messages can be there, if we can actually bundle multiple messages together and try to make that to make this transmission more efficient that way. And also we're working with situations when it's possible that the network is down for a long time, so the car keeps driving, keeps gathering data, but it's not able to send the data. So for that, we have implemented some back pressure strategies where, depending on the amount of data that gets collected on the car and is not sent yet, we can actually reduce the amount of data that we collect in the future until we are able to send the data. Okay, and moving on to the cloud side. So these are three parallel approaches of working with the data in the Azure cloud that we're experimenting with right now. So the first one, the one in blue, as I mentioned, we've got a Kafka cloud currently running in Azure Kubernetes service. Data can be stored there directly. It can be kept there indefinitely. Kafka is a very good solution for receiving large amounts of data fast and storing them. The disadvantage for Kafka is that it does not have indexing, so we need to actually then process the data. Working, for example, we've got services in multiple languages, following a microservice architecture, again running on Kubernetes there, that are able to look at the data that we receive and index it, do any kind of pre-processing that is necessary. For example, the indexing we're saving now in a Mongo database. So yeah, Kafka is a good solution for stream processing. So it can react, the consumers can react to the data we receive really fast and prepare it. Also an advantage with using this is that we control every part of the process. Of course, that can also be a disadvantage. We need to handle the scaling of the cluster. If we need to increase the number of Kafka nodes, the number of processors, we need to handle that ourselves. Another architecture that we're looking into is of working with Azure blobs and also Azure Queue Storage. So Azure Queue Storage can't receive very large messages. I think it's up to 64 kilobytes, which means we can't really store images if we get images from the car. So we are limited there. That's why we need to use Azure blobs for the raw data. But we also need to look into Azure Queue Storage to try and see which of these two would be a better trigger for the Azure functions, which then we will use to do the processing of the data. So again, in parallel to the above model, the Azure functions would be the ones that are responsible with pre-processing the data, extracting any kind of metadata we need, indexing that, storing it into a Cosmos database, which is the solution from Azure. So we're also thinking about looking into some time series database. Posted here is InfluxDB, just to experiment with this. For example, for merging data. So if we've got data from different signals that may be sent in over different messages, we may need to actually merge that data, associate the different signals, and an easy way to do that may be to just store the signals at their respective timestamps in a time series database, and then we have the data synchronized already. For this architecture here, so these are all services that are managed by Azure for example, for Azure functions, they will handle the scaling for us. So that's an advantage. We can then just focus on implementing the solution that we need on the code that we need. We don't have to worry about boilerplate code. We don't have to worry about scaling. But currently, we don't know if the performance can be tuned as well as it would be with a solution that we implement ourselves from scratch with Kafka. And the last architecture I'm going to go over that we're looking into is putting now our data into Azure blobs with Data Lake Storage Gen 2. So this is a storage in Azure that's specifically tuned to work with the Synapse Analytics Data Lake, which is Spark. So it's Apache Spark. Actually, it's the Delta Lake solution. So it's let's say an evolution of Spark. So this Delta Lake brings the lakehouse architecture, which wants to be like a combination between a data lake, which contains just unstructured data, and a warehouse where structured data lives that has already been processed. So this tries to put the two things together and try to store them in the same place. So we're already working with Spark with in other projects here, and we know that Spark can handle large amounts of data, even connectivity data sent from the cars. But it's more, so Spark was developed for working with batch data, and doesn't work as well with streaming data. But the promise for the Delta Lake is that it would be better also at streaming data. So this last solution, again, we are using a system that's managed by Azure. They will handle the scaling of the Spark cluster. We don't have to worry about that. The advantage for this solution would be that it may be easier for people that aren't necessarily developers to get in and contribute at this part. For example, data analysts, which are more they're more used to, for example, writing SQL. You can do that with Spark very easily. Yeah, so these are 3 architectures we're looking into now. They're still in development. We are working on also comparing the results we get. We need to understand exactly what are the advantages and disadvantages of these 3 to see which is the best way to go forward for this. And of course, so all this process here links back into the training of models that Andrei presented at the beginning. So once we have our data securely in the cloud, it can be used, and yeah. Okay, so I think that was all. Also, the time is almost up. If there are any questions.
Okay, very good presentation. Thank you, Silvia and Andrei. I'll keep Silvia. So let's say, so like a real case scenario, how much data do you usually get from a test car or production car to the cloud? I mean, if just to get an idea, like. It's a terabyte, it's 3 megabytes. How much is it?
Depends how much you drive with the car.
Okay.
Do you know, Andrei, do you know an estimation for?
Yeah, so the let's say per minute, it's at least 15 gigabytes.
Wow, that's a lot.
Yeah, but it can go up to, I don't know, 30, 35. It depends also on what's collected.
And we talk here about all the sensors from a car.
Yeah, all the data collected in that minute.
Wow. Okay. That's interesting. Yes, and you have many cars, right? But
of course.
And this is more for development, not necessarily for production. Or it's also for production.
What do you mean production or
I mean,
development? So this is for this is the
go on, sorry.
so if you imagine that all the cars running in the world will be able to produce the data, they will be able to produce the data, but we won't be able to get that. Yeah, this is for improving the algorithms and the models. So it's not technically possible even now to get all this data. It's not technically possible to get it via internet. So
makes sense.
So the internet is not enough.
Okay, and how did you? I mean, okay, let's say you get the data, and then I suppose you delete it or you store everything.
As I said, this is a challenge always. So
Okay.
It depends what we want from that data, right? So yeah, you never delete important data. You could, as a good strategy would be to delete data that is not needed anymore. Or if we have, as I said, I given that example with the Windows Media video, then you can have the Windows Media video and the frames, right? So that would be a duplication of data. You know, there can be strategies involved not to duplicate the same data, the same images after all. No, but other than that, this depends from use case to use case, and yeah, data is pretty valuable. So
I agree, and then this data can be used by a virtual ECU that we got previously the presentation and do some more simulation, I suppose, right?
It could, yeah. In the end, it can.
Theoretically.
So, yeah.
Okay. Good. Okay. Great. Thank you, Andrei. And I think that's all from my side. The audience is already pretty quiet already, so yeah, that's fine. Okay. Thank you very much. And next, let's go to our
Thank you.
next.
Thank you.
Thank you, Silvio. And hi, Mihai.
Hi, can you hear me?
Yes, very well, and we can see you very well. Okay, so the stage is yours. Let me put the slides on.
Thank you. Thanks for having me. I'll briefly introduce myself. So my name is Mihai Souca. I'm a software engineer at Bosch. And for about 5 years now, I work in automotive steering systems. So today I will do a presentation about functional safety in automotive steering systems. So safety is a pretty boring topic for 6 p.m. on a Wednesday, but I will take my best to make it fun. So what I'm gonna do, I'm gonna introduce you to what is the steering systems, how it works. Then we'll go to see why this system is safety critical, how can we assess the criticality or the level of how do we measure how critical it is, then see what measures can we take to make it safe for production, so to say. And if we have time at the end, we'll go through a little practical example. Okay, so let's get going. Okay, so a steering system is the system that helps the driver turn the wheels. The weight of the car makes the steering by the force of the driver really difficult. So we need some kind of power element to help us steer safely. So the hydraulic power was used for quite some time, but for now the state-of-the-art system is using an electric motor. So we have there a brushless electric motor, which is measuring the force the driver applies to the steering wheel and calculates a force that it should apply to the wheels so the driver turns the wheel safely. So this is the steering system in a nutshell. There are a lot of ways of doing that, depending on the size of a vehicle, depending on the application, but this is the main idea. So now I think you all have an idea what safety is, but there is, of course, a standard to tell us what exactly is meant by that. So ISO 26262 is the standard in which regulates the automotive safety, or the functional safety in road vehicles. Okay, so the definition goes like something like this. Functional safety is defined as the absence of unreasonable risk due to hazards caused by malfunctioning behavior of electronic systems. So what I highlighted there is unreasonable risk. You cannot get rid of all the risk in such a complex system, but what you can do is to take measures to identify potential risks and take measures to make it reasonable or to make it unlikely. Okay, so in the modern cars, to enable this automated driving and all these intelligent things the car does nowadays, you need a lot of intelligence, a lot of sensors, a lot of actuators, and a lot of processing power. So a lot of electrical components are integrated into these vehicles nowadays. So of course the complexity is very high and things can go wrong. And when the things go wrong, the life is endangered, both for the passengers and for the how do you call it, pietoni? Whatever, the people on the street. Okay, so
Pedestrians.
pedestrians, thank you. Okay, so let's see what's the reasoning of assessing the risk and risk reduction. So first of all, we have malfunctions. Things happen with electronic devices. For example, in memory, there can be a certain area corrupted due to electromagnetic interference or whatever. So a lot of things can happen. Then there is a hazard, which is potentially turning into a risk to the driver. So we have to identify all these risks correctly and kind of quantify how dangerous are they, and then decide what are the mitigation mechanisms we can apply to make sure this risk doesn't actually cause damage. So this is the chain of implications. Now let's look at this well-known matrix in safety, and I'll introduce you to the AC level, which means Automotive Safety Integrity Level. And this is a measure for the criticality of a certain scenario. Okay, and we have here a matrix that helps us assess the safety integrity level of a certain scenario based on three parameters. Okay, you see them: severity, exposure, and controllability. So first of all, severity, it will tell us what kind of damage would this scenario cause. If it's something manageable, light and moderate injuries, like I don't know, bumping your head on the headrest or pinching your finger at the window, and goes up to life-threatening injuries like going out the road at 100 kilometers per hour or things like this, or braking when you're not supposed to, and things like this. Okay, this is the severity, is the first parameter. The next one is exposure, and here it's important because we might have a really dangerous scenario, but it can be really unlikely to happen. So we have this exposure parameter, which is telling us how likely is this event to happen. for example, if we'll see in the next slide an example and how these parameters work, but certain scenarios might be very unlikely. So even if the scenario is really serious, it might not need a lot of countermeasures exactly because it's very unlikely. Okay, and the third parameter is the controllability, and this tells us how easy can a driver manage the situation. So if it's an easily manageable situation by a normal driver, it will have a C1, so to say. But if only certain drivers, more experienced drivers, can handle the situation, it would be a C2, and C3 if it's really uncontrollable. So like the car is accelerating by itself and there's nothing you can do. Okay, and if we assess all these three parameters, we have a result of what is the safety integrity level of this scenario. Of course, this is slightly subjective. So when these things are discussed, a lot of safety managers are discussing together and arguing back and forth if on what is the correct level for this scenario. Okay, so let's go further and see some actual examples how this is calculated. And we took some from steering, of course, because we talk about steering today, and we're talking about oversteering, for example, when the wheels are turning, when the car is turning more than the wheels are supposed to turn it. And we have, for example, oversteering at between 15 and 100 kilometers per hour on the main road. It's a dry road, and the exposure, you see we have an E4, which means it's very likely you're driving on a main road dry between 15 and 100 kilometers per hour. It's most of the driving situations. So we of course have an E4 for this, and we have a C3 because this is a really serious situation, and oversteering can cause. It's really difficult to counterpart it. Okay, and we have an S3, which of course can cause critical injuries both for the driver and for the other traffic participants. So we of course have an ASIL-D for this scenario. But you can see the same thing, oversteering, when parking. So we are at less than 10 kilometers per hour on a side road. We have a QM, and this is because the exposure is still high, but the criticality is simply controllable. So the car can be easily stabilized by a driver, and the severity, if it's not stabilized by the driver, it will cause some light injuries like a bit of discomfort or a little panic. But yeah, so that's the same thing can turn out to have two completely different AC levels depending on each scenario. Okay, so this is just to exemplify it, and let's go further and see. After we decided, okay, this is my product, I want to develop steering systems. Apparently there a lot of things can go wrong, and we need a lot of mechanisms to reduce the risk of these things happening. And for that we need kind of an checks, like assessment, some kind of argumentation that this product is safe to be put on the roads. And this compliance with the safety integrity regulations are made of three main parts, and we'll get into each of them from now. So first is the seal capability, which is more about the process you are following. So the things you do to develop a product, in which way, and how traceable are your activities, and how well documented is all your work. This is a systematic capability. This has to be well prepared and well taught. Then we have the architectural constraints, which are more about what mechanisms does your architecture implement or gives you to use to tackle these scenarios or these risks. And the third one is the probability of failure, which is more like focusing on reliability and metrics that can measure how likely is for a product to fail from harder parts, so to say. Okay, so we need to get to take care of all these three. You can just have a well-defined process and have a really robust hardware if you don't have any mechanisms in your architecture to tackle the risks of all the other combinations. So you can have a robust hardware and some good mechanisms if you don't have a well-defined process and good traceability of requirements and how they are interfering and interacting. It's hard to go to an audit and say, I know what I'm doing, it's fine, we have these mechanisms, we have this hardware, nothing can go wrong, because you won't be compliant. Okay, so let's see. First one, seal capability. As I said, we need traceability, and this is the famous V model of software development. It goes on also for hardware and mechanics, not only for software. But the main idea is you have to have a top-down decomposition. So starting from a high-level technical safety concept, which then translates to more and more specific requirements for each component, which of course have to be validated at each level. So this kind of traceability gives you gives your process the power to envision and to have a better picture of your safety argumentation and to have a better argumentation for audit and things like this. Okay, so this is the seal capability or systematic capability. In steering, we have a pretty well-defined process with well-defined roles and certain steps needed to be done for a small change in the software to get an easy approval, so to say. And this is the first part of the compliance. The next thing is the architectural constraints or the mechanisms that are implemented. And here we have a lot of mechanisms. I just mentioned here some of them. Built-in startup tests, which you have to check all the electrical components that are functioning, all the switches and the memory, everything you can check at startup. You have to automate it and do some good startup tests. Then, of course, we have on an electric motor, we have to protect the output stage. So there's a lot of things that can happen. We have high temperatures in the steering sits under the motor. So the heat and beside the heat from the steering itself, there's a lot of heat to be dissipated, and we have to protect the output stage of high temperature, of high power densities, and things like that. We have a lot of memories, and we have to make sure we store critical data redundantly. So if some data is corrupted, we detect it and react to it. End-to-end protection, of course, because the steering system communicates with a lot of different ECUs and receives and sends critical data, which has to be protected somehow. And these are mechanisms to ensure the integrity of the data transmitted. Okay, diverse design, which means a safety critical algorithm or logic you need to implement. It's advised to implement it twice and have a second component confirm what the first one had at output. So we have two same thing implemented, which confirms the other one. And if some output is different, we have to react to it and don't send it further. Okay, this is not needed if you have, for example, a dual controller or a dual core controller which functions in lockstep mode, because this is kind of implicit to it. Okay, we need the centralized error handling. We have, for example, we have about 300 errors that can be logged. So you need to prioritize them and react to the most critical one, then make sure the other errors that are coming in the system do not override or do not take the light out of the main problem which happened. So you need to have a good error handling mechanism. Program flow monitoring. This is an operating system timing mechanism which assures that the functions or the runnables are called in the exact meant order. If for example, as I said before, there are two functions that calculate the same thing, and the second one, if has a different output, will trigger a reset. It would be bad if the second one was called first by the operating system and then the first one, because then we might have a false positive. So we have program flow monitoring to ensure the exact sequence meant to be executed. And we can, as an architectural decision, we can go for a non-preemptive task concept. So the critical paths are not interrupted by some other task. And this has a disadvantage. Oh yeah, I'll go to a second. I forgot to press the next slide. This is a photo of a diverse design. So we have a function which outputs something, but the input goes to another function which then compares the output to the first one and triggers error reaction or triggers something. It doesn't have to be necessarily an error reaction. We have to keep in mind the availability of the system. So if you can just shut up and don't pass it over, it's fine. You don't have to do a reset or things like that. Okay, and as I said, we got to the preemptive, non-preemptive operating system discussion. Here, if you have a preemptive system, you have a better responsive system. Depends on application, but you have a lot of context switching, which is consuming time and resources. You can go for a non-preemptible system, which has a more defined structure. It's a little less responsive, but it works for this. We have something like best of both worlds, and we have a cooperative scheduling operating system, which is basically a non-preemptible system, which at certain points in time, it can pass on the microprocessor to another task. So the rule of thumb is every 100 microseconds, we check if there's something more important to be executed, and we say, okay, take it over from here. We don't get interrupted, but we periodically check if there's something more priority with more higher priority. Okay, so these are all architectural things you can decide for your project to ensure some better reactions to certain kind of risks. And this is just to show you how the system works. So this is a graphic of the maximum assist torque. So this is mainly the visible output of the system. So we have 100% assistance. System can help you steer at full capacity. Then you can see a fluctuation. There might be some reductions of this level depending on temperature and voltage. Then there can be a fault happening. For example, a MOSFET is burned, or I don't know, a communication cable is tear down, or God knows. Then we have to detect it. This is the first thing. We have to automatically detect this fault and react accordingly. Then if the fault is not something critical, we can continue providing the 100% assistant torque. If there's something that physically disables the motor to provide assistance, we will reduce the level, for example, 50% here in the degraded mode, and we can continue like this until the end of the driving cycle. But if there's a second fault, we might not be able to provide assistance anymore, and in this case, we at least don't want to sudden drop it. We want to ramp it down if possible. So this is kind of how we want to, how the user wants the system to behave. Because yeah, I didn't say it in the introduction, but as a safety way of thinking, we want our system to work, of course, as intended. But if something happens, we want to fail in a predictable manner. Okay, so we want to fail in a predictable manner. This is really important to keep in mind. Okay, so back to at the third thing. I think I'm a bit off the schedule. I'll try to rush it. So we have the probability of failure, and we have certain metrics to measure reliability, and one of them is the fit rate, which means failure in time, and it's roughly translates to the mean time to the first failure. So in this, it's judged upon 1 billion hours of functioning. So if the devices on average are failing after 1 billion hours of functioning, it will have a fit rate of 1. Okay, and the higher it is, the less reliable it is. And here's an example how to calculate it. As a curiosity, the diode has a nice 1 fit reliability measure. Okay, and the state-of-the-art electric motor we have for automated driving is achieving a 10 feet rate. And here you can see it in the picture. It's fully redundant. Everything is redundant. You can see it has 2 power supplies, 2 communication, 2 torque sensor inputs. And in the next slide, I will show you a brief diagram of how it works. So we have 2 controllers which are running in parallel. It's not a master-slave system, it's a primary and secondary, so both controllers are operating at the same time, and they have each one its own sensor to measure the force by the driver, then has interprocessor communication to coordinate on the control of the motor, for example, and transmit other information. Then we have 4 output stages for the motor. So each controller has 2 output stages. It's like you will have 4 motors in one unit. Okay, so this is why you have 12 phases, 12 coils. Okay, so this is a fully redundant system, and with this you have a way low probability of failure. And yeah, this is the system currently used to enable automated driving up to level 4. I think I have a slide on that. Okay, so putting all these 3 together, this is taken from the Bosch official site. We have this steering control unit which we can sell to customers, which enables them to have a reliable control unit for steering system in automated driving scenarios. Okay, I think we are not in time for the example, but I'm waiting for your questions. I will briefly go through this. Okay, we have a meme, of course, the unavoidable. I think I missed it. But yeah.
Okay, thank you.
Thank you.
Saying was very complex presentation. Thank you, Mihai. Do you use, for example, in order to predict the failures, do you use also AI algorithms?
No.
Or, no.
There's,
so it's just signal processing.
Yeah. There's no machine learning currently in steering systems.
And at some points you mentioned an interesting issue like inverse steering. Is this happening in your table? There was like oversteering, and then on top of
in the table it was not about really the steering system, but about another component mounted on the steering column, which imposes another angle over the steering wheel angle. So it might go in the other way and things like that. But it's for example, it might happen. Actually, I'm not. You can. There is a variable which tells the part of if it's a left drive car or a right drive car for the control of the motor, and if you put that wrong, and you might end up having a positive feedback loop, and you have to shut it down pretty quickly if you.
I see. And let's say if you discover an issue with the steering wheel, are you shutting down the car or what's happening? Well, I mean, I never heard such things, but just theoretically, if your steering wheel is not working properly, what might happen?
So if things go wrong, you have a decision table, how critical it is, and hopefully you can still provide some assistance level. The driver gets a yellow lamp in the dashboard, and he's able to steer the vehicle safely on the side of the road, and then just call the things.
Okay.
But there might be cases where you cannot provide assistance anymore, and in this case you have to at least ramp down the level of assistance so you don't have a sudden loss of assist, which would be a safety violation.
I see. Okay, yeah, very interesting domain. Okay. Yeah, so I think with this we are finishing the entire event.
It was really fun.
Yeah, I hope our the online participant got fun. Actually, we got some more questions, but I'll just send them probably separately. Couldn't ask all of them. Okay, so yeah, thank everyone for Bosch Future Mobility Talks, and see you next time. Bye.
Thank you. Bye.
Thank you. Bye.
Bye.
Bye.